applications of the vector equation to speed, time, and velocity. So we sort of get our kinematics fix in vectors as well. Uh-oh. That's probably what I, yeah, don't use Internet Explorer. All right. So vector equation, here's our vector equation. R is the position vector of any vector on that line. A was any point on the line, and B was our direction vector, and T was some sort of scalar. Now, we're going to apply that same idea with speed, time, and velocity. Now, R is still going to be the position vector of any point on that path, but A is going to be the position vector of our starting point. T is going to be time. So if it makes sense when time is 0, that A would be what would be left. And that would be your starting point, because your starting point is when time is 0. B is your velocity vector. Instead of calling it a direction vector, it's your velocity vector. So if your vector was 2, 5, that means that in one time, you're going to go 2 to the right and 5 up. And then if you take the magnitude or length of B, that's the speed that you're going, because it's going to figure out the distance that you're going to travel in 1 unit of time. So that'll be the speed of your object. So here we have a moving object with the following vector equation. 1, -1, so that's your starting point. It's starting at 1, -1, plus t 3, 4. So 3, 4 would be your velocity vector. You are traveling in every 1 unit of time, and time is in hours here, so in every hour, you're traveling 3 kilometers to the right and 4 kilometers up. So our velocity vector is that 3, 4, and the length of that velocity vector, because if you imagine this would be 3, this would be 4, a squared plus b squared equals c squared, that would be 5. You're going to travel 5 kilometers in 1 unit of time, and since time is in hours, you're traveling 5 kilometers per hour. So we can describe this in words. The object starts at 1, -1, moves in the direction of 3, 4, at a speed of 5 kilometers per hour. So if we wanted to take our vector equation and change it to write it in ax plus by equals c, which is sort of similar to y equals mx plus b, it's like a linear equation that you would have dealt with before. There's a couple of ways you could do this. One way is to use your vector equation. From your vector equation, you could write your parametric equations. And then from your parametric equations, solve for t. And you would get your Cartesian equations. Once you get your Cartesian equation, which no longer has the t in it, it's just a matter of rearranging to get it in the form that they asked for. Now this is the usual way when dealing with a vector equation, how you can go from a vector equation back into a Cartesian equation and rearrange it into any form that you would like, just with x's and y's. Of course, you could have used your old skills. There's our starting point, 1, -1, over 3 up 4. there would be another point. Using your grade 10 math, could you find the equation of that line? And if you could find the equation of that line, could you rearrange it to look like ax plus by equals c? Yes. So that would be another way. Although in this case, we want to get familiar with all of the forms of a vector equation so we can manipulate them and move back and forth. So here we've got the parametric equations for x and y. Time is measured in seconds and distances are measured in meters. We could write down our vector equation. Again, this is a vector, so I should underline it or put an arrow over top of it. And then our velocity vector is the 5, negative 2. So if we find the length of our velocity vector, that'll be our speed. Root 29, if we wanted to put our units here, it's meters per second. So we can sort of imagine this is two-dimensional. So you can kind of imagine someone running along the ground here, and you're looking from above. And you set up some sort of coordinate system where they start at 4, 5, somewhere on your coordinate grid, and they're traveling in this direction, 5, negative 2, at a speed of root 29 meters per second. So you're maybe up in a tower watching this person run around. And you notice that they're running in a straight line, and that there's a pole located at 39, negative 9. Will they hit the pole? You're kind of watching them, and it sort of seems like they're going on a pathway to hit that pole. How do you find out? If we plug in the 39, negative 9 in for r, what we're really trying to find out is that point on the line or not? If it is on the line, then there's going to exist a value of t that makes that work. And that value of t is exactly when, how long after they started, they're going to hit that pole. So you set up your parametric equations for your x and your y coordinates. And when you set up your parametric equation, you can just solve for t. So when I solve for t in the first one, move the 4 over and divide by 5, I get t is equal to 7. When I do the same thing in the second equation, in your y-coordinate equation, and solve for t, I get 7 again. Since those are consistent, you know that that person is going to run into that pole. And the time is going to be 7 seconds after they started. Now, we can move into 3 dimensions. And this is where, like flying in the air, often you're going to be using 3 dimensions. Person running along the ground is often using 2 dimensions because it's kind of flat. But an airplane, you'll often need to use a 3-dimensional vector to describe it. So we've got a jet flying at a speed of 700 kilometers per hour in the direction of 2, 6, negative 3. We want to find the velocity vector. So the difference between equations of lines and stuff with just a direction vector, the direction vector could be any multiple of things. But when we want to apply it to speed, velocity, and time, we want that direction vector to be our velocity vector. So if we look at 2, 6, negative 3, and we look at how long is 2, 6, negative 3, it has a length of 7. So if that was our velocity vector, then it would only have a speed of 7 kilometers per hour. We want the same direction, but to have a speed of 700. So you might be able to see a shortcut at this point. If it has a speed of 7, what would I have to multiply by to get a speed of 100? 700? Oops, gave away the answer. To multiply by 100, and that would work. But there's going to be some where the number's not going to be nice. Like, let's say it just ended up as square root of 39, not a number that is even easy to multiply by to get 700. What could you do? Well, you could find your unit vector. And your unit vector will have the same direction, but will be only going at a speed of 1 kilometer per hour. So when we think about our unit vector, it has a length of 1, and in this case would have a speed of 1 kilometer per hour. And then, if you wanted 700 kilometers an hour, you could multiply that unit vector by 700. It would still have the same direction as you had before, but now has a length of 700, so it would now have a speed of 700. So can you see from your original vector of 2, 6, negative 3, if you multiplied that by 100, you would get 200, 600, negative 300. And that's a little bit of a shortcut in this case because the number 7 and 700 are easy to multiply to get each other. But you're going to get some examples where that's not the case, in which this will be the best method. Find out your unit vector. You know that that has a length of 1, and then whatever speed you want, you just have to multiply by that. A yacht leaves a harbor, and we've got a vector equation for our yacht. And we also have a cargo ship. Notice that there's the same value of t in both of these equations. So the starting point for the yacht is 0, 0. And that's because 0, 0 is the harbor. The starting point for the cargo ship is 6, 3. So the cargo ship is not at the harbor while the yacht is at the harbor. But it's traveling in the direction 3, 7, and the yacht is traveling in the direction 5, 8. So how fast is the yacht going? We'd take our velocity vector of our yacht, find the length of it, root 89 kilometers per hour. Sounds faster when you say root 89, but it's like not that fast. Just over 9 kilometers per hour. Got a little crazy here with my synonyms. Does yours say yacht or does yours say pleasure boat? Okay. Find the distance of the cargo ship from the harbor when the pleasure boat starts its journey. So that is, we know that it starts at 6, 3. That's at time equals 0. That's where the cargo ship is. At time equals 0, the yacht is at the origin at 0, 0. If you want to find the distance between 0, 0 and 6, 3, that's just the length of 6, 3, which is the square root of 45 kilometers. So the cargo ship is just under 7 kilometers away from the harbor when the yacht leaves. Now you're going to start to see the theme of today's class. If both the yacht and the cargo ship continue on the same courses, when will they collide? It's much more fun to make things collide than have them narrowly miss each other. So what do we know? We know our two equations. And from those two equations, we can set up our parametric equations. And our x parametric equations, if we equated them, that means that 5t would have to equal 6 plus 3t. And 8t would have to equal 3 plus 7t. Solving both of those equations, you get t equals 3. So what probably happened here? I mean, the cargo ship is big. It was probably on autopilot and just traveling. The yacht was a pleasure boat, so they're having way too much fun and not watching where they're going. And the cargo ship just went blip. And the last question. So we have our unit vectors, 1, 0, and 0, 1, going 1 to the east and 1 to the north. O being the origin is where there is a lighthouse. And that lighthouse is not visible if you're outside of that circle. There's a ship initially 31 kilometers west and 32 kilometers south. So on our diagram, that would be at negative 31, negative 32. The radius of that circle is 25 kilometers. So currently, the ship can't see the lighthouse. The ship is moving parallel to the vector 4, 3 at a speed of 20 kilometers per hour. An hour after leaving P, the ship is at point R. Write down the vector OP. Well, that's just negative 31, negative 32. This is where vector questions can get a little tricky here in part B. It says, show that the path of the ship can be represented by this equation. Now, the negative 31, negative 32, that can be argued easily because that's your starting point. So you could say, I know that my starting point is negative 31, negative 32, so I have that. The 1612 is what? That's your velocity vector. So we know the direction the ship is going in. The ship is going in 4, 3 in that direction, but we need to show that it has to be 1612. We also know the ship's speed is 20 kilometers per hour. So what we're going to need to do is find our velocity vector. Okay? The most common mistake in this kind of show that question is you use 16 and 12, and you show that the length of 16 and 12 is 20, so it must be right. And you show that 16 and 12 is parallel to 4, 3, so it must be right. Okay? The problem with that is you're using your answer to show your answer. Does that make sense? And that's what you're supposed to show your answer. And so you can't say, oh, here's my answer, here it is, see, it's right. You have to get that 1612. You can't use the 1612 to show that. You see how the negative 31, negative 32, I mean, it's in the equation as well, but we knew that information from before. We knew that our ship was there, so we can use that information. We didn't know the 1612. So what we're going to have to do is we're going to have to think about what do all the things in our equation stand for. There's our starting point, which we knew was negative 31, negative 32. B is our velocity vector. And so we're going to have to see if we can find our velocity vector. Now, we know our direction vector is 4, 3, and the length of 4, 3 is 5. So that means if the velocity vector was 4, 3, it would be traveling at 5 kilometers per hour. So from that, we could find our unit vector by dividing by 5. And then once you have your unit vector, if you want to find your velocity vector with a speed of 20, all you would need to do is multiply that unit vector by 20. And so what you've done is you've shown that the velocity vector has to be 1612, rather than using the 1612 to show that it works. And then once you've got your 1612 and your starting point, you can say, therefore, my equation must be negative 31, negative 32 plus t, 1612. So find the vectors OR and PR. Well, to find OR, we're told that O to R is on the path after 1 hour. So if we put 1 in for t and simplify this equation, we get that O to R is negative 15, negative 20. If we want to find P to R, again, just draw out. Here's O, here's P, there's R. If you want to find P to R, does it make sense that you could do that by going from P to O and then O to R? As far as our vectors are, P to O, that's the same as just negative P, and O to R is just the same as R. So P to R will just be R minus P. And if you put in R, which was negative 15, 20, negative 15, negative 20, and you subtracted negative 31, negative 32, you'll get 1612, which should make sense because what have we done? From P to R was just traveling 1 hour, and how far do we go every hour? We go 16 to the right and 12 up. So it should make sense that P to R would be the same as our velocity vector. Show that, so another show that question, when the ship reaches R, the lighthouse first becomes visible. Well, we know that R is negative 15, negative 20, and the lighthouse is at the origin, 0, 0. If we figure out the distance between them, which is the same as the magnitude of O to R, we find out that that is equal to 25. Since the radius of when you can see the lighthouse is 25, you can say R is the point where the ship first becomes visible. There's a happy face. We are all done. Here. Sorry. That was... One more question. Here we go. Oh, of course, we have to keep with our theme. Second ship's path can be described as follows. Determine if the boats will collide. Now, in yours, does yours have an S or does yours have a T? S. Yours has an S as well. Okay. So if we put our parametric equations here, we've got one equation with T, one equation with S's. And if you put both of those together, you get two equations with two unknowns. So we'll often have on the IB exam or in questions this simultaneous equations appear in the middle of a question. Very often with parametric equations where you have two different variables and two equations. And so now what we have to do is use either substitution or elimination. Substitution or elimination to solve for one of our variables, and then we can solve for the other one as well. So in this case, if you multiplied the first equation by a -3 and the second equation by a -10, or if I would redo this, I'd probably multiply the second equation by 10 so I could add instead of subtract. And then you subtract those two equations, you're going to get t is equal to 4. Yeah, I would probably just change these to plus signs and add them instead of subtracting. It's always easier to add than it is to subtract. Yeah, I'm looking at what I did wrong here. This should still be, there we go. If I multiply the second equation, if I multiply the first equation by a negative, then this should be a plus, right? And this should be a plus. Take that first equation and multiply it by -3. Those would both be positive. Take the second equation and multiply it by 10. These would both be negative. If you added your equations, this would be a negative there and a negative there. You still get t is equal to 4. And once you have t equals 4, you can choose either of the two equations, equation 1 or equation 2, and solve for s. And so you get s is equal to 4 as well. And so they will collide at the point at the time of 4 hours. So not only did you have to be able to solve for them, but the two values had to be the same, because it could have been that the two boats crossed paths at different times. But since they cross paths and happen to cross paths at the same time, they're going to collide. And that collision is going to happen at 33:16. Scrolling down. Here we go.